Hello, my name is Praveen. Today, I and my colleague Jordan will be presenting our research on site-specific management in precision agriculture. So let us begin by understanding what is a precision agriculture. It is an advanced innovation and site-specific management strategy used in farming to assist in making management decisions such as increasing crop yields, quality, saving costs, reducing environmental hazards, etc. In a more simpler words, instead of treating the whole field as a single unit, precision agriculture seeks to break down the field into smaller manageable units by observing, measuring, and responding to agricultural variables such as soil properties, yields, terrain attributes, etc. In our research, we used several years of yield data to study how yield varies spatially and temporally in a specific field in an attempt to provide a tool that can be used to make decisions at a much finer scale. In addition, we explored Soil Survey Geographic Database or SURGA data to examine the relationship between soil characteristics and yield patterns using machine learning. A bit of a background. United States is one of the largest producers and consumers of agricultural commodities in the world. In 2021, nearly 0.7% of US GDP was contributed by the output of American farms, whereas about 5% of it was contributed by industries that rely on agricultural commodities. Therefore, it is extremely important to continuously grow agricultural productivity. Precision agriculture holds a great promise in this area of increasing agricultural productivity by providing finer scale management choices with different characteristics. However, when optimizing these management choices, the spatial and temporal heterogeneity of characteristics in a specific field often presents enormous challenges. That brings us to our two primary research objectives. First is to identify the management zones within a farm by performing a spatiotemporal yield variability analysis and develop a generalizable algorithm that could be used to perform such yield variability analysis in various geographical contexts. Second is to examine the predictors of yield by studying soil characteristics data via machine learning. We used a 5-year harvest data from Brent Southern Earth Farm, Oklahoma that was provided by our collaborators from USDA Agricultural Research Service. The dataset consists of various attributes such as yield volumes and moisture, location, etc. that was derived from the combiner or the tractor every second. We followed this particular study process where we collected the yield monitoring data from the USDA Agricultural Research Service. Then we collected some soil survey geographic database that was openly available. Then we did some data pre-processing. Then we performed this spatiotemporal yield variability analysis on the clean data. And then finally, we also did some yield prediction via machine learning. As part of the data pre-processing, we first identified the outliers in yield monitoring data using a threshold of mean plus or minus 3 standard deviation. Then we imputed those outliers using an inverse distance weighted method, which is particularly suitable if we want to preserve the spatial properties of the data points. When doing the imputation, this method gives more preference to the data points that are closer to the outlier than the points that are farther away from the outliers. Then we did a grid sampling, which is to divide the whole field into a set of 20 meter by 20 meter grids and computed the yield volume for each individual grids. Next, we aggregated this grid level information of the yield monitoring data and also incorporated information about soil characteristics from SURGA data at the grid level. We then performed spatiotemporal yield variability analysis. We visualized the grid level yield plots for all the years to see if there were any noticeable patterns in the data. We then computed descriptive statistics for each year of yield data. From these statistics, it appears that the yield varies significantly by crop type over the years. Since our analysis is focused on zone level yield monitoring and not on a specific crop type, we normalized the data by computing z statistic for each grid I for all 5 years. This way, we could use different crop yield data to identify management zones. The next major challenge was in incorporating spatial and temporal information to develop an interpretable visualization or tool for decision making. We wanted to capture the yield volume at a grid level and visualize variability in different zones. This way, a farmer would be able to identify zones that need extra effort in producing higher yields. To capture this information, we created 6 groups. We categorized volume into three groups: high, low, and mixed. If for all the years the yield is above or equal to average yield in that year, we consider it to be high yield zone. Whereas if it is below average yield, we consider it to be low yield zone. Then if for some of the years the yield is less than average, and for others if it is above average, we consider it to be mixed. To measure variability, we divide it into two groups: high and low variability. If the maximum difference of z value of yield volume over the years exceeds a threshold delta, we consider it to be highly variable, and vice versa to be less variable. We made an interactive visualization to change the delta value and observe variability patterns. The 6 groups were formed by pairing each category of measuring volume and variability. Then each grid I was classified into one of the 6 groups, as you can see in the image. The left plot shows the zones classified into 6 groups, where we set the maximum variation of yield over the years to be 1. The right plot shows the variability when it is 2. This plot can be used by farmers in making management decisions, such as how much fertilizer to use in a specific zone, etc.
Hello, I'm Jordan. I'm going to be discussing the yield prediction section of our research. For this part, we wanted to explore the impact that SSURGO data has on the farm's yield. And SSURGO stands for the Soil Survey Geographic Database. It looks like this. There's a very elaborate map of various soil types. Each of these has their own attributes like flood frequency or available water storage. What we've done is taken this data and overlaid it onto our farm of interest, and we end up with something that looks like this. So you can see in this farm we have 3 different soil types. Here they are labeled. And when we consider the yield, we wanted to group the yield to better visualize it into 2 categories of low and high. We did this using natural breaks classification machine learning method. And this is the results of it. We can see that most of the low yield is on the right side of the farm, which appears to be because of this particular soil type. If soil type was a perfect predictor for yield, we could expect to see something like this, where the rightmost polygon produces 100% of the low yield in the farm, while the other 2 produce the high yield. And it's not a perfect predictor, but we can see that it's got to about 95%. So these results were not as strong for other farms that we tried, but further research could be done to see why particular soil types produce low yield more than others.
To conclude, a spatial temporal yield variability analysis at the grid level was conducted for identifying management zones in a specific US farm, where a new method for evaluating the grid-based variabilities using z-statistic was developed and used. Second, a customizable and user-friendly tool for yield variability analysis was developed, and it can be used in other different farms as well. So our case study of yield prediction showed that the soil type could be a key contributing factor to the yield volume, as they were highly correlated. Some of the limitations of our research and the approaches that we used is the criteria established for grid categorization are conservative, resulting in less flexibilities in defining the management zones at different spatial scales, such as we have discrete categories for volume and variability rather than having it on a continuous scale. Maybe that could be an improvement in the future. Also, the same yield prediction method did not perform well on other farms. For future work, we'd like to improve the methods for identifying management zones such that more meaningful information can be obtained for informed decision making. And also we could include other predictors such as terrain attributes and weather data in yield prediction, and also use more advanced machine learning algorithms and feature selection techniques to improve the prediction accuracy. Thank you.